Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about op-amp circuits, so let's get started. Alright everybody, so let's talk about a basic op-amp circuit. Let's draw the op-amp right here, shall we? Alright. Now let's suppose we have inverting here and you're non-inverting here, okay? So you're inverting. Let's say first it just goes to ground, okay? And let's say this one that just goes to a sine wave, alright? And here's your output. What's going to happen to your output? This is your V out. V out. This here is your V in. Well, let's draw a picture of it, shall we? So if we draw ground, here is your ground of the output, alright? I just call this ground. Now, if we draw your sine wave, let's take your sine wave that comes up. It's the top part of it, right? Here's the bottom part. Let's just draw the top part again. Okay? Now, here's what happens. Think about it. When your non-inverting input is at a higher voltage than your inverting input, your result is going to be high, isn't it? So at this point, it's above, it's going to saturate. This point right here, I'm going to just call it VSAT for V-saturation, right? We've already talked about that. Now, but at this point, it crosses zero again, doesn't it? When it crosses zero, your non-inverting input now is below your inverting input, isn't it? So this is going to go in this direction. Until such time that your non-inverting input voltage is above your inverted input voltage, and it's simply going to go up again, right? So if you look at it, your output is going to be what's in black, okay? It's going to be high and then low, and high and low. So that's what it would do to the output, okay? Now let's take this one step further, right? Let's put a voltage here instead of ground. Instead of ground, now we have a battery, right? And suppose this is at V reference. But by the way, you can create your reference voltage any way you like, all right? You could use a voltage divider, which you all know how to do. So this V reference can be created in many different ways, but let's just look at it with a battery, okay? So at this point, let's redraw the ground. Here's your ground. I'm going to redraw. I'm going to draw your V reference here. This is V ref. This is ground. Let's draw your wave again, shall we? Goes up, down, up, down, right? Now, remember, your inverted input now is connected to V reference. So when your non-inverting input has a larger voltage than your inverting input, occurs now at this point, doesn't it? And right here. And right here. And right here. So look at the effect of this. What happened? This part here between these 2 points, by the way, it would come up here like this. Then at this point it would drop down here. Actually come down a little lower, I'm sorry. Come down here like this. Then it would come up here like this. Come down here like this. So what would happen here is that this part here would get smaller. I should actually draw it like this with arrows pointing in this way. It would squeeze it. It would get smaller. And this part here, between here and here, this would get wider. You see what happens there? The higher this voltage went, you noticed it would get smaller and smaller and smaller. Now, what would happen if the Vref voltage was negative? Well, if it was negative, obviously this part here would get smaller, right? And these parts that got smaller before, well, they would get wider, all depending on where your reference voltage was. Rather interesting, isn't it? This is basically just comparing 2 signals to one another, and you can see how it can affect the output waveform quite dramatically. All right, so next I'd like to talk about noise and how noise would affect this circuit. See you soon. All right, so let's talk about noise and how this would affect a comparator. Suppose now we have a similar circuit, right? Here's your op amp. Here's your non-inverting input. It's going to ground, right? And here's your, I'm sorry, I said that wrong. This is your inverting input going to ground. And your non-inverting input, this is going to be in, okay? And suppose your signal that's coming in is supposed to be a nice sine wave, just like this, okay? Let me see if I can draw this line. I'm going to make it in red. This is your ground, okay? So, what happens in the case that this signal is noisy? Bring this down here just a little bit more like that, right? Down. Okay, so suppose now instead your signal goes up. It just has noise. I'm trying to draw it as best I can, but you get the idea. It goes noisy, it's noisy. So in other words, this is what we're interested in. What happens at the transition? Do you see it crossed right there, and it also crossed right here, and it crossed right here again? That would have made some transitions there, more than one. We want just one transition, right? But when it makes, it could make, well, it could go high and low, then high. So it would make an extra transition there. And you don't want that. So what that would do then, your output, literally, it would be low here. When it crossed first, it would go high, then it would go low, then it would go high. It might do that several times and then stay high. And you know what? The same thing could happen here. It could go low, up, however long. I know it's exaggerating it a little bit, and then it would stay low. So in other words, every time it crosses the transition point, look, if you have noise, it could cause multiple transitions, right? That's what we're worried about. And that is what we're going to try to resolve here. So think about it. How would you resolve it? And one method of doing this utilizes this circuit, okay? Let me show you what the circuit is. So now what we're going to have that part right there is going to be V in, okay? And this part right here is going to be fed back from the input. So you're going to have this. All right, and this is going to be your V out. So you might notice something different, that the input is now fed into the inverting input, right? So let's figure out, when is this thing going to trip? So when it trip, when's the transition going to take place? Well, the transition is going to take place when Vn is equal to this non-inverting input voltage, right? And that's right here, isn't it? Now, if you look at it, you have two resistors. Let's call this R1, R2, right? So that voltage, I'll call it the upper trigger point, is going to be equal to R2 divided by R1 plus R2. That's the simple voltage divider formula, right? Times V out. And that's going to be the max because it's saturated, right? That's what that volt's going to be. Because remember, what we have here is that's the transition point where both of these points are going to be at the same voltage, isn't it? Now, when you look at it, when this voltage is rising, suppose it's looking like this. I'm going to use part of a sine wave again. In other words, it's going in this direction and it's continuing, right? So at that point where it reaches this trigger point, that voltage, what's going to happen to your output voltage? This one, let's draw the line. Your output voltage is going to change, isn't it? It's going to drop. Got it? So what's happened now is, why does it drop? It's because your non-inverting input has a higher voltage than your inverting input. So now what's your new voltage? You're going to have a lower trigger point, aren't you? That's going to be the same out, except your V out's going to be negative, isn't it? So it's going to be a negative voltage. So you could have multiple transitions up here, right? It's close to where it's transitioning, but it's already made the transition, and this voltage has changed. So now you aren't going to have that switch bounce, all right? Because it's not comparing it to the same value once it makes that initial transition. So it's going to basically stay here, and then this is going to come down, going to keep going up and come down, and then at some point it's going to cross this again, all right? And at this point, your inverting input voltage will be less than your non-inverting voltage, and when that happens, whenever that happens, you're going to have a rise, right? You're going to have another transition. Got it? And it's going to continue to operate like that. But notice, when your voltage goes up, it transitions down. When your voltage then comes down to that point, it transitions up. So that's the difference here. In this method that's used here, the term is called hysteresis. All right? So that is a method that is used to address noise for this kind of circuit. All right? That's one of many ways to address noise, but that is something that can be used, and it is used sometimes to address noise to make sure that it doesn't affect or minimizes the effect on the output. All right? So what actually, though, is hysteresis? Hysteresis equals your V minus your V. All right? That's your hysteresis. And you know both of the equations to figure it out. V out max for upper trigger point, for V lower trigger point, if it's, lower trigger point, that's going to equal R2 divided by R1 plus R2, and this is going to be minus V out max minus V out max. All right? So that is one way to address noise. All right, folks. See you soon.